This section explains the Proximal Policy Optimization (PPO) model and code implementation. Let's first look at the PPO model overview. Proximal Policy Optimization is an on-policy method, meaning it updates the policy using data collected from the current policy. The key innovation of PPO is the use of a clipped objective function to limit the size of policy updates and stabilize training, preventing large and unstable updates. The goal of PPO is to maximize the expected return while keeping updates within a safe region to avoid large changes in policy. Actor-Critic Architecture. PPO uses a neural network with two components. Actor. This part of the network represents the policy and outputs actions based on the state. Critic. This part estimates the state value function, providing feedback to the actor about how good the current state is. PPO, objective function. The core idea behind PPO is to use a surrogate objective function that approximates the expected return of the policy with a clipping mechanism to prevent overly large updates. The general form of the PPO objective is as follows. Theta are the parameters of the policy. RT is the probability ratio between the new and old policy for action AT taken at time step T. This is the ratio of the probability of taking the action A in the state S under the new policy compared to the old policy. Accurate T is the advantage estimate at time step T, which tells us how much better, or worse, the taken action was compared to the average. Epsilon is a small clipping parameter, typically between 0.1 and 0.2, which ensures that updates don't change the policy drastically. The clipping mechanism helps to ensure that the probability ratio does not deviate too far from 1, thus preventing the policy from changing too aggressively in a single update. The objective function has two components. 1. Unclipped surrogate, which encourages the policy to increase the probability of good actions where the advantage is positive. 2. Clipped surrogate, which prevents the ratio from increasing beyond a certain limit, ensuring stability. Value loss. In addition to the policy loss, PPO also includes a value loss to improve the critic's state value function estimate. The value loss is the mean squared error between the predicted value of the state and the true return, target value, as follows. V theta is the value predicted by the critic, state value function. RT is the actual return, target value, for the state at time t, often computed using bootstrapping or Monte Carlo estimation. The value loss encourages the critic to better estimate the expected future reward for a given state. Entropy, regularization, exploration. In order to encourage exploration during training, PPO includes an entropy loss term, which discourages the policy from becoming deterministic too early. High entropy indicates more exploration, and low entropy suggests that the policy is exploiting learned strategies without exploring new actions. The entropy term is given by as follows. Pi theta is the probability distribution over actions under the current policy. The negative log probability encourages exploration by penalizing deterministic policies. It helps the agent avoid local optima and ensures that it does not settle on suboptimal actions too quickly. Total loss function. The total loss function for PPO combines the policy loss, value loss, and entropy loss as follows. C1 and C2 are hyperparameters that control the relative weight of the value loss and entropy loss. The policy loss is the primary term, while the value and entropy losses help stabilize training and encourage exploration. Now we implement the PPO code. PPO network class. PPO class. Testing the PPO model.